Welcome to the video about peak broadening in chromatography. In this video, we are going to see what are the factors that make peaks broad in chromatography, and we are going to look deep into the one diameter equation that describes the peak broadening in chromatographic systems. So the first factor that can make peaks broad in chromatography is called eddy diffusion. Or it can also be called multiple path length diffusion. And this comes from the fact that when we look at our chromatographic columns, then the columns we have are filled usually with particles. And these particles are packed as efficiently as possible into the column. So let us see one example column here, which is packed with different particles. So let's say we have a column something like this. So now let us assume that we have two different compounds that belong to, or two different molecules belonging to the same compound. So we have here two molecules. We denote one with red and another one with green, but they are of the same compound. So they have the same chemical structure. And let's for a second assume that these compounds do not interact with the stationary phase at all, so they are not retained. So the question is, how could these compounds pass through the column? And we can see that, okay, maybe this green molecule enters the column and it flows through these two particles, and maybe then through these two particles, and here and here and here. It goes fairly straightforward through the column and then exits the column somewhere over here. Now, the red molecule starts also from the beginning of the column, but from a slightly different point. And what can start now happening is that this compound may, go here to the left-hand side first, travel around these particles from here, and then from here, and then from here, and then maybe exit also from here somewhere. So what we see is that the green molecule went through the column with a fairly straight line, while the red molecule traveled a much longer path to pass through the column. And therefore, even though they didn't interact at all with the column particles, with the stationary phase, these two molecules belonging to the same compound, it took them different time to pass through the column. So when we look at the chromatogram and we have a peak for this compound, then the red molecule came out somewhere later on this peak, while the green molecule came out somewhere earlier. So the same compound, but the time it took for these two molecules of the same compound was different, and this was due to the fact that the way they traveled through the column was different. And this is called eddy diffusion. And you might now think, what are the factors that influence this eddy diffusion? Eddy diffusion is usually denoted in one diameter equation with an A, and it depends on the particles. So the better the particles are packed, the better the more uniform is the path that the molecules are traveling. So the more similar are the paths for all of the molecules that they are traveling through the column. So of course, it's easier to pack the column if the particles are very similar to each other. And the more round they are, the better it is. So it is the particle shape is very important. So the more round the particles are, the better it is. But it is also the diameter of the particle that is very important. The larger the particles are, the more likely it is that the paths of the molecules of the same compounds will be vastly different. So the smaller is the diameter of these particles, the smaller will be the effect of the eddy diffusion, so the less different will be the paths of the same molecule through the column. Now, the difference in the paths that the molecules take to travel through the column is not the only source of peak broadening. Also, just simple diffusion plays role in the peak broadening. And actually, there are two different ways diffusion is important. And the first one that we are looking at is longitudinal. Diffusion. Longitudinal diffusion, as the name suggests, is the diffusion that happens during the passing through the column in the longitudinal direction of the column. So when we have the compound that is traveling through the column, then of course it moves through the column, but also it's not only that the mobile phase is carrying our compounds through the column, but this compound can somewhat diffuse in the direction that is opposite to the mobile phase flow direction or slightly diffuse forward relative to the mobile phase flow direction. So we can see that some of the molecules may get in front of the mobile phase and some may get a bit behind, simply due to the fact that they diffuse either in the mobile phase flow direction, but some of them diffuse in the forward direction while some diffuse in the backward direction. And this diffusion is usually in one Vector equation denoted by B. So B denotes longitudinal diffusion, and longitudinal diffusion depends on the diffusion coefficient in the mobile phase. So we can denote it with the dm. So the higher is the diffusion coefficient in the mobile phase, the more peaks broaden due to the diffusion in the longitudinal direction. So this means that mobile phases which are very viscous have lower diffusion coefficients, and peak broadening in these mobile phases from the longitudinal diffusion perspective is not as important factor in peak broadening as it is from mobile phases that are much less viscous. So from this point of view, it would seem very good idea to have to use mobile phases which are very viscous, so that the diffusion in the longitudinal direction would not impact our peak width. However, in reality, this is balanced out by the other diffusions that play a role in the chromatographic systems, as well as the pressures that are required to uh, push the very viscous mobile phase through the column. Lastly, there is also another important factor that that has a role in peak broadening, and this is resistance to mass transfer. And to understand this, let us look closer into the process of retention in the column. So let me draw here a zoom in of two particles that are our stationary phase. And usually these particles are covered by the actual stationary phase. So they very often have an inert core, and then they have something like a more actual retention causing phase. So in case of gas chromatography, these are immobilized liquids. In case of liquid chromatography, these are either layers of water, for example, in case of normal phase and helichromatography, or they are just liquid-like acting layers, for example, in case of reversed phase chromatography. So let's say we have these layers here, and for the stationary, on top of the stationary phase carriers, we have for both particles. And now we also have our molecule that is traveling through the column. Now, in this resistance to mass transfer, it is very important to think how the retention actually happens. And for the retention to actually happen, what needs to occur is that when the molecule is traveling through the column, it needs actually to diffuse to the mobile phase, stationary phase, border. So it actually needs to be able to become in contact with the stationary phase. And this, of course, depends on the diffusion coefficient in the mobile phase. So the less the mobile phase is resisting diffusion, the more efficiently the molecules are traveling to the border of the stationary phase and mobile phase from the mobile phase. However, when the molecule is already in the stationary phase, then it also needs to diffuse back to the border to be able to move on in the column. So to be passing through the column. And this now depends on the diffusion coefficient in the stationary phase. So here are two diffusions that need to happen. The first diffusion is that the compound needs to diffuse from the mobile phase to the border of stationary phase and mobile phase. And there is also, when it is now already in the stationary phase, it also needs to diffuse back. So both these are very influential. So why is that important? This comes from the fact that if we have now two molecules again of the same compound, and the green molecule is here being retained by diffusing to the stationary phase and mobile phase border, but the red molecule here is just traveling a bit further. So what happens is that if it takes very long time for the green molecule to diffuse to the border and then diffuse back, then the red molecule travels very, very far. So that means that the green molecule and the red molecule are separated in the column very much. So the band of this compound in the column becomes very broad. And this is also a reason why the peaks become broad in the chromatography. So therefore, the resistance to mass transfer, which we usually denote by a C in the one-diameter equation, it is depending on the mobile phase diffusion coefficient, but it is reversely proportional to it. So we would like this we would like the diffusion coefficients to be large for and very efficient transfer of the compounds from the mobile phase to the stationary phase to occur. And we would also like the diffusion of the molecules back from the stationary phase to the mobile phase be as efficient as possible. So from the mobile phase point of view, we see here that in the longitudinal diffusion, we had a case where we wanted the mobile phase to be quite viscous to avoid longitudinal diffusion. Then here, in this, from this aspect, from the resistance to mass transfer point of view, we would actually like the mobile phase to be have a very low viscosity to make the transfer of the molecule from the mobile phase to the stationary phase as efficient as possible. Now, there are also other factors that are playing a role here, and this is how well our column is packed. So, of course, when the column is very well packed, then the distance that the molecule needs to travel is shorter. So when the particle size of the stationary phase is small, then the mass transfer, peak broadening due to mass transfer is also smaller. So we want to have a well-packed column with small particles here as well. And another important factor is how wide is the stationary phase. So how thick layer of stationary phase we actually have. So we can say that the width of the stationary phase on this inert carrier is a D with a subscript S, and the smaller this layer of the stationary phase is, the shorter distances our molecules actually need to transfer to need to travel to actually transfer between the mobile phase and the stationary phase. And therefore, again, the peak broadening due to the resistance of mass transfer is smaller when we have a lower, a less thick layer of stationary phase in our column or on our column particle. Now, last but not least, these factors also have a different impact based on the flow rate that we are pushing the mobile phase through the column. So one diameter equation is actually about the relationship of the theoretical peak height relative to the mobile phase flow rate. And we denote the mobile phase flow rate here with a U. And we had these three different factors that affect eddy diffusion, longitudinal diffusion, and resistance to mass transfer. So first, we could think, how does the eddy diffusion influence the peak height with the flow rate? So in eddy diffusion, the eddy diffusion captured the fact that different molecules of the same compound travel slightly different routes through the column. And this is actually something that is flow rate independent. So independent of the flow rate, the eddy diffusion coefficient is the same for the compounds. Now, when we have longitudinal diffusion, then the longitudinal diffusion is actually dependent on the flow rate. And the faster the mobile phase is passing through the column, the less time do the molecules have to diffuse longitudinally. And also the mobile phase is flowing so fast that the molecules are kind of focused. So the impact of the longitudinal diffusion is decreasing with the increasing mobile phase flow rate, and it is a roughly exponential decrease. And lastly, we also have the impact of the resistance to mass transfer, and this is actually increasing with the flow rate. So why this is so? This is because if our flow rate is increasing, then it becomes increasingly hard for the molecules to transfer to the surface of the mobile phase and stationary phase, to the border of the mobile phase and stationary phase, where the compound can transfer from one phase to another, become retained, and then come back. So the faster the mobile phase flowing, the more impactful the resistance to mass transfer is. And therefore, as a result, the sum dependence of the theoretical plate height versus mobile phase flow rate looks something like this. And this is known as the one-temperature curve. And it can also be written as a general equation where the theoretical plate height is expressed by all of these terms, and the generic form looks something like this. So reversely, it is independent of the eddy diffusion, but reversely proportional to the longitudinal diffusion and linearly proportional to the resistance to mass transfer. So this actually shows us a few things. It tells us what kind of column we would like to have, what kind of a chromatographic system we would like to have. Firstly, because both the eddy diffusion and the resistance to mass transfer depended on the particle size, and they also depend on how well the columns are packed. Eddy diffusion, the most of us. Resistance to mass transfer also depended on what is the thickness of the stationary phase. So we know that we don't want to have too thick more stationary phase as well. And we also know that the mobile phase diffusion coefficient is important, but it has a reverse effect on the longitudinal diffusion and on the resistance to mass transfer. Resistance to mass transfer also is affected by the diffusion coefficient in the stationary phase. So these are the key factors that are important in getting a very good chromatography. So if we could summarize, then we could say that we want to have small particles in our column. We also want to have it well packed. So the column would be well packed and would not have any voids that would cause differences in the path that the molecules take in traveling through the column. And we would also like to have not too thick stationary phase layers. And we need to optimize the mobile phase diffusion coefficient. So we don't want to have too viscous mobile phase, but we also don't want to have too low viscosity mobile phase, because these are both influencing both the longitudinal diffusion and the resistance to mass transfer. So generally, a good column is a small particle column that is well packed. However, we will see later that the columns don't definitely need to be packed, but still the same factors will then also influence the performance of the chromatography. And this is something we will see in case of gas chromatography for the capillary columns. Now, one more thing that we could see here is how to choose now at which mobile phase flow rate we would actually want to do the measurements. You could think about it for a second. Okay, so maybe just to remind you that to get efficient chromatography, we wanted to have low peak widths at the half height. And this was related to the number of theoretical plates, which is also related to the theoretical plate height inversely. So what we want to have is as many theoretical plates as possible. So we want to have high number of theoretical plates, which means that we want to have as low as possible theoretical plate heights. And just to remind you, the theoretical plate height can be thought as the distance that if this is my stationary phase particle and this is the molecule, then we can think of this as the distance that the molecule travels between two retention events. So if I'm here having retention events when the molecule is being retained and then again released from the stationary phase, then the theoretical plate height can be viewed as this distance between these two events. So this, we can think of this as the theoretical plate height. So the distance the compound travels in the column between two retention events. And we want it to be as low as possible to keep our peaks very narrow. So here, in this case, we can think of this that we would like to be somewhere over here where the minimum is. So this minimum plate height is what we want to get. So getting somewhere here. However, sometimes we can go slightly higher on this plateau, maybe somewhere here, where there actually is not very much of a rise in the theoretical peak height, plate height, but we could do the analysis, for example, 50% wider. But definitely we want to be somewhere here in this plateau region where the theoretical plate height is minimal. You definitely don't want to work somewhere where the plate height is very high. So these are not optimal for the analysis. And actually, the big question in the production of chromatographic columns is how to obtain columns which have as minimal plate heights as possible, and also which have the plate heights profiles against the mobile phase flow rate, which have this nice plateau minimum here. So for which the optimal flow rate range is quite wide. So these are important questions in developing chromatographic columns. Shortly, this was about the way peaks become broad in chromatography, and we viewed this on the example of particle-filled column. It is fairly similar for capillary columns, and we will have a look at this further for the capillary columns once we talk about them in the gas chromatography as well. So these videos were the introduction to chromatography, and we'll continue with gas and liquid chromatography in the upcoming lecture.